Okay, class, this is our final video lecture in our chapter on gases. And here we're going to talk about non-ideal behavior, that is, deviations from the ideal gas law. And we will introduce what is called the van der Waals equation. In reality, gas molecules do occupy some space. Remember when we talked about a mole of a gas at STP condition occupying 22.4 liters, and then we said, but if those molecules were really condensed down to a condensed liquid phase, they would occupy a little bit of volume. In the case of water, maybe 18 milliliters. So we said that maybe in reality about 1,000th of the space available is actually occupied by the gas molecules on average. So one of the reasons for deviations will be that the gas molecules actually do occupy a little bit of space. The second deviation is due to the breakdown of another tenet of the kinetic theory of gases, which is that the gas molecules collide elastically with one another or with the sides of the wall. That is, an elastic collision is one in which they just bounce off perfectly and they don't stick together in any way. And in reality, there is some stickiness, which we will talk about. The collisions are not completely elastic, especially when you go to very low temperature and very high pressure. Now, let's think about these conditions of very low temperature and very high pressure. If we either increase pressure and push the gas molecules together, or if we lower temperature so that the volume decreases, then the gas molecules are going to get closer and closer together. So any interactions that they have with each other or any volume that they actually do occupy will become more significant. Okay? Let's consider a plot of pressure divided by RT versus pressure itself. Now, pressure divided by RT, if you think back to the ideal gas equation, that should be PV divided by RT should be equal to M, the number of moles. So if we had 1 mole of a gas, let's say any of the gases that are in this slide, nitrogen or methane or hydrogen or carbon dioxide, if we started with 1 mole of these gases at STP conditions, for example, and then we increase pressure, well, if the ideal gas equation applies, then still PV divided by RT should be equal to 1, and we should have a perfectly horizontal or flat plot. But instead, what is observed is that if you increase pressure to some very high pressures, that you see deviations. If you actually measure pressure and volume and R and temperature, R is just a constant, of course, that in fact what happens is you get plots such as the ones shown. Some really funky looking plots. Some just go linearly up, some dip and then go up again. So there are definitely deviations from ideal behavior, but these deviations, again, only occur at very high pressures or at very low temperatures. And our reality is closer to the left side of this plot where the pressure is like 1 atmosphere or so. And if you notice this plot, the deviations really don't show up until you get to much higher pressures. So, deviations from ideality can be observed at low temperature and high pressure. A person named Johannes van der Waals proposed the following equation, which corrects for this non-ideal behavior by including 2 additional constants, which we will call A and B. Now, let's look at the equation below. This is PV equals nRT, but the pressure, in that first parenthesis, the pressure has a term a constant A, which we'll come back to, times the quantity N, that's the moles of gas, divided by the volume, that quantity or that ratio squared, so A times N divided by V, quantity squared. That is the P, the pressure term of the PV equals nRT, and then you have the volume term, but the volume term has a correction to it. It's volume minus some number, minus N, the number of moles, times the second constant, B. So PV equals nRT, but you have these 2 corrections applied. The first correction and the first constant, A, is related to the stickiness of the molecules. That is, when the molecules actually collide with each other, they do sometimes hang around for a brief period of time because they interact with each other. Likewise, the gas molecules can interact a little bit with the walls of the container. The second correction and the second constant, the B constant, is related to the actual atomic or molecular volume occupied by the gas molecules or the gas atoms. Now, these two constants, A and B, can be experimentally determined for many gases, and when they are used, this equation can then correct for the deviations we saw in the previous slide. This slide shows a table of some of these A values and B values, these constants that are corrections to the gas law that are what are called van der Waals constants for gases. Now, something that's interesting is that the B value primarily tracks the size of the gas atom or gas molecule. That is, for smaller gas atoms or molecules such as helium, the B value will be smaller, and as you get to larger and larger molecules, which is as shown in this table, the B value will increase. So that's one rationalization for these B values. It actually makes some sense. Smaller gas molecules or gas atoms have smaller values for B. The A constant is related to this stickiness, which later we will refer to as intramolecular interactions. And it can vary a great deal, as you see in this table, from 0.03, a pretty small number for helium, up to something like 20 for carbon tetrachloride. It is due to these interactions, and we will see later on that some molecules interact with each other much more than do other molecules. This is for a later chapter, but we will talk about such things as dipole-dipole interactions and dipole-induced dipole interactions and induced dipole-induced dipole interactions. The latter we sometimes refer to as van der Waals interactions, the same Johannes van der Waals. And we will see that these interactions between molecules actually have an electrostatic basis due to some separation of charge in the molecule, whether that separation is permanent or is just transient. But that's for a later chapter. One final just note, I suppose, is we've seen Johann or Johann's name come up quite often, so I guess that means that if you are interested in your son or daughter becoming a famous scientist, you might think of Johann or Johannes as a name, or maybe the English version of John, or if it's for the feminine, maybe Johanna or Joan. Just something to keep in mind, because there seems to be an awful lot of Johann or Johanns that we've talked about. Okay, this is the end of this chapter on gases. See you later.